So, but I do want to kind of continue on here, talking about sort of stoichiometry and limiting reagents. Obviously, it's a very important sort of topic. First off, though, again, I showed you this, which I'm imagining is probably a fairly new approach for most of you. First off, any questions about sort of the ice table and where everything came from, why we did everything there, and how to kind of use it. Now, as I mentioned earlier, there's really kind of a number of different approaches that you could take to solve sort of limiting reagent problems off the top of my head. I know like at least three different sort of methods. I will say that probably if you learned it in the previous class, this is probably not the method you learned. Again, you probably learned, I would say nowadays it's pretty popular, the like I was describing before, another approach. So I just want to talk about a couple of different approaches that you could take to these problems. And again, it may be one that maybe you've learned before. Another very common approach, like I said before, is pretty much taking each of these reactants individually and just doing a stoichiometry problem like we did previously, that we call kind of like a basic stoichiometry problem. And for example, you would start with 124 grams of aluminum and convert it to moles of aluminum, then do the mole to mole relationship between aluminum and your product, and then convert those moles of the product into grams. Then you would do a separate stoichiometry calculation starting with the 601 grams of iron 3 oxide, convert it to moles, and then go the mole to mole relationship to the product and convert those moles into grams. And through this method, what you're looking for is, once you do again those two separate calculations, you're looking for whichever one would produce the smaller number of grams of product, which in our case we already know is going to be 234 grams. So one of those guys, which would be the aluminum, would produce 234 grams. The other one would produce more than 234 grams. And in that method of determining limiting reagents and all that, again, you would look at the one that produced a smaller amount, and that would be the aluminum in this case. And that 234 grams would be your theoretical yield, and aluminum would be your limiting reagent. Again, perhaps a downfall to that method is if you wanted to then figure out how much iron, you would have to go back to the beginning again and start with the aluminum and to the iron to figure out how much iron you would produce, where we could do it relatively quickly in this method and figure out that. Also, you typically would then have to go back and do a separate stoichiometry calculation to figure out how much of the excess reagent was left over again. So that's just sort of the drawbacks. It's not a big deal to go back and sort of start from the very beginning. It's only an extra step or so. And that's a perfectly fine approach if that's the way that you were taught limiting reagent problems and you're happy with doing it that way. Let me be very clear, you're absolutely welcome to continue to do those problems that way. You do not have to do the ice table if you don't want to. Again, it's just more of a convenient way of doing these type of problems. So if you've learned an alternative method, which is, I'll put it this way, a legitimate method, not one you made up yourself, but a legitimate method, you could obviously continue to use those. You don't have to use the ice table. I just showed it to you because, again, it's a very convenient way to answer all the questions. And it is something that you'll do a lot if you are continuing on to 200B. It'll be a little bit different 200B, but same certain general idea. So ice table method, the individual reactants to product method is another common way to do it. And I have worked out here, I think, a third way, which is another common way that we can do these. The idea here, and sort of the third common method that people are taught, is you basically convert the grams of each of the reactants into moles. And basically what you do is a calculation to begin with that basically says that if you want to use up 100% of one of the reactants you started with, how much of the other reactant would you need to put in there? So for example, here they chose to do, we'll just go by what they chose here. they choose here? They chose to go with the 124 grams of aluminum. And what they're going to do is a calculation, and it's a stoichiometry calculation to say, if I want to use up 124 grams of aluminum, which is all my aluminum, how many grams of the iron 3 oxide would I have to put in there? So they would convert the grams of aluminum to moles. They would do the mole to mole relationship between the two reactants. And again, the goal is I want to use up all of this. You know, how much of this guy do I need? And then they're going to convert that guy into grams. And this calculation tells them that if they wanted to use up all of the 124 grams of aluminum, they would have to put in there 367 grams of the iron 3 oxide. At this point in this sort of method, what you do is go, all right, if you look at the problem, that is my starting amount of aluminum. That is my starting amount of the iron 3 oxide. So based on this calculation, if I want to use up all the aluminum, I need to put in there 367 grams of iron 3 oxide. Do I have enough? And the answer is yes, you have enough, right? Obviously, if you started with 601 grams, but only need 367 grams, you have enough of the iron 3 oxide. And what that calculation would tell you is because you have enough, that means that that is the excess reagent, like we determined previously. And by default, the aluminum, again, would have to be our limiting reagent. And that's basically what they're saying here. So this is a very, very common approach of how to do limiting reagent problems. Actually, this is the way I was taught years ago, is to do a calculation like this where you basically are comparing the two reactants, and you're basically saying, if I want to use up one of the reactants completely, how much of the other one do I need to do there? You could also do it mole to mole as well. You could stop here and compare moles to moles, but you know, you could go all the way to grams as well. And in this method, once you do that calculation and you determine that aluminum is their limiting reagent, then you do a separate stoichiometry problem where you start with the aluminum. And now you figure out how much product you would produce, because again, as we talked about, it is our aluminum, which is our limiting reagent, that determines how much product produced. Right? So it's this guy. So that is, again, a very common method that you first do the calculation between reactants to figure out which one's the limiting reagent. And then once you determine that, you go back to the starting amount of the limiting reagent and you do a stoichiometry problem to figure out how much of your product you would produce. Again, slightly downside to this is if you wanted to know how much iron, like we did before, you then would have to again go back to the 124 grams of aluminum and do a separate calculation. If you wanted to know how much of your excess reagent would be left over in this particular case, you would be okay because of the one you chose, because you know that you had 601 grams started with, and you need 367 grams, so you could actually just subtract these two. So this method is sometimes a little bit better than the one where you do two separate calculations to products, because if you need to answer that excess question, if you picked luckily correctly, you could actually answer it. If you didn't pick correctly, you got to go back and do another calculation. So they all have sort of benefits and, you know, maybe downsides, I guess, in terms of the calculation. But, you know, like I said before, I'm going to show you ice table way probably in these next few examples. Again, I think is a beneficial way, but if you're more comfortable doing it, either the separate calculation to the products and which one's the smallest, or like we just talked about here in this example, using the reactants to figure out which one's the limiting, and you're comfortable doing it that way, you absolutely can continue to do these problems this way. You don't have to do the ice table. The good news is, as long as you choose a legitimate approach, one of the three we just spoke about, you should end up with the same answer regardless of which way you kind of do it. Any questions on any of that there? Okay. So again, a reminder that when we are dealing with limiting reagent problems, we could really identify them as what is there when we look at the problem, we have enough information to get the moles of each of our reactants. And again, at that point, you need to do one of the steps. So next thing we're going to talk about here is yields and different types of yields. So we sort of touched upon one of these guys, which is our theoretical yield. And our theoretical yield is really the kind of maximum amount of product that you should produce. It is sort of based on the equation. So for example, the previous problem we just did there, I think we got 234 grams of the aluminum oxide. That would be the theoretical yield. The theoretical yield is, again, based on how much you start with and the equation. If everything went perfectly good, perfectly well, nothing went bad, it is technically, in theory, how much product you should produce, hence the theoretical yield part of it. In reality, things don't always go perfect, as you probably are aware of. And that is where we have, again, another type of yield, which is referred to as the actual yield. And much like the name sort of implies, the actual yield is actually when you physically went and did the experiment, you know, how much product you produced. So when we talk about yields, by the way, it is about products. So you don't have a theoretical yield of reactants or anything like that. So when we say yield something and talk about yielding something, in sort of chemical equation talk, the arrow can sometimes be referred to when you have your reactants and your products. In word speak, the arrow can sometimes mean to yield. So when we talk about yields, you know, it's products is what we're talking about. So theoretical yield should be how much products, actual yield should be how much products were produced. So the actual yield is really, again, how much you actually produce when you did the experiment. The good news, in a book type problem, this is usually given to you. So obviously in a kind of book type problem, you know, it's usually given to you right there in the problem. Obviously, if you're doing the experiment, you would physically, you know, measure that amount out. So we're going to do, you know, if you did like an experiment like that, obviously, you know, for example, when we did like the silver chloride experiment, you know, when you got that final weighing of your evaporating dish was the silver chloride, and you figured out how much mass of just the silver chloride you produced, that was your actual yield, right? So that's, you know, how you would get into the sort of laboratory aspect of it. And like a book, textbook problem, exam problem, quiz problem, that number is typically just sort of given to you somewhere in the problem. It'll say, hey, you produced this much. Putting both of those together gives us a yield that's sort of important. It gives us a pretty good understanding of, you know, how good or bad perhaps our experiment went there. And that is the percent yield. And in the percent yield, we take the theoretical yield divided by, the actual yield divided by the theoretical yield times 100. In terms of units, usually it's grams over grams. You technically could do moles over moles as long as they're both the same units, but usually it's grams over grams times 100. When we do percent yield, we're looking for a high number here is good. And by a high number, I mean, you know, near 100% is really good. In most case situations, you probably won't get 100% yield. Maybe again the 90s or something like that, which is really good. If you did an experiment where you got like 10% yield, that means that was pretty crappy and you probably spilled stuff along the way or something bad happened. You know, you lost something there along the way. So, you know, usually, again, percent error, sometimes people get confused by the percentages here. When we've been talking about percent error is a number where we want small is really good, large is bad. But percent yield, we're looking at how well we sort of did this. How much did we actually produce in this experiment? You know, was it very close to, in theory, how much we should have produced? So we're looking for a high number there. Again, in the 90s or high 90s, very good. Not so good, very small numbers. Could you get over 100% yield? And the answer is, in reality, yeah, you could get over 100% yield. Is that a good thing? That's not a good thing. It probably means you screwed up somewhere. So, usually, you don't want over 100% yield. That's not usually such a good thing. It usually implies that, you did something wrong, incorrectly. So, one very common way that people sometimes get over 100% yields. So, for example, we were talking about a couple of days ago about precipitation reactions. So, let's say you took two solutions. And as we know, we can take two solutions that has no solid and mix them together. And you make a solid, right? Nice, wonderful red solid, I suppose. Now, you have this precipitate, right? And you're interested really in how much of the precipitate you made. So you take like a funnel. I'm going to try to draw that funnel-ish. You take a funnel-ish type thing here. And you pour out your solution with your precipitate, obviously on some filter paper. Liquid part goes through. Hopefully you got something there to collect it. And obviously the solid part ends up on the filter paper, right? And you take out your filter paper, got your solid on there. Yay. And you decide, cool, done with the experiment. I'm going to go weigh that. Right away, you're just going to go take that filter paper and weigh it. What is the problem with that? The problem with that is you're really interested in how much of the solid product that you made. Now, if you remember from our picture here, there's a liquid part, right? And that liquid part is coming through and being collected. Solid parts being collected on a filter paper. But if you ever poured something that is wet through a piece of paper like filter paper, you know that, it wets the filter paper, yes. So if you're impatient, which sometimes happens in real life and experiments, and you decide, I'm just going to take that filter paper and put it on the balance and get the number that you get for the weight of your solid is going to be the weight of your solid, but it's also going to be all that excess water that's there, right? So you have all that extra water weight, which you're going to count as basically your product. And what that's going to do is make this number be bloated with water, if you will, too big, and you will end up with over 100% yield, and you technically did the experiment bad. And that's why typically in a process like this, before we weigh it, we dry it. And you could either dry it in like a drying oven, you could just let it sit in your drawer a couple of days and let it dry out, and then weigh it. That way, you got rid of all that excess water, and what you are weighing is really just your solid and not all that excess water weight. So I will say in reality, you can get over 100%. And usually I would say in most cases, if you do get over 100% yield, it's actually not a good thing. It probably meant you screwed up somewhere along the way. So that's why I say, pretty much a pretty good percent yield is, in the 90s, mid 90s, high 90s is a really good percent yield. In most cases, you usually won't get 100% yield in most cases. And that's because if you just think about logically as well, even in this aspect, forget about the part where you were rushing and you didn't wait for it to dry. But if you've ever experienced taking like a precipitate like that's a solid and a liquid and pouring it out, you probably have witnessed a lot of things like, there's like a smear of solid that just won't come out or something, especially if you're in a test tube or something like that. Maybe it gets caught in the bottom corner. So you lose a little along the way, perhaps some of the solid, actually goes through as well. Maybe, you poured too much or too quickly on that filter paper. It went up the sides and down through the bottom. So very often when people filter things, they see some solid kind of going through, which again is not a good thing. So there's a lot of room for, even if you're extremely careful, just the process of, doing things physically usually results in some type of error happening, which means you usually can't get perfect 100% yield every time. And that's why, in the high 90s is really, really good. That's almost perfect. There's always some type of things that happen. And in addition, there's even things that you can't necessarily control a lot of times. There could be some side reactions that occur as you're doing these reactions that, you don't have too much control over, and it's going to take away some of your yield. So in most cases, getting perfect 100% yield doesn't always happen, and going over 100% yield does happen. And sometimes you may think that's cool. I did like 200% better than everybody else. It just meant you kind of screwed up 100% more than everybody else. So that's not necessarily a good thing. Any questions on the different yields here? All right. So obviously the theoretical yield would come from the equation. And if it's not given to you, you would have to do a stoichiometry problem like we've been talking about to figure out the theoretical yield. And then again, the actual yield would be given to you and you could calculate the percent yield. So why don't you take a few minutes here and start working through this one and see what you could come up with. What is the percent yield in this reaction? If we have started with 2.4 times 10 to the 7 grams of TiCl4, molar mass from the periodic table, 189.7 grams per mole, reacts with magnesium from the periodic table, molar mass 2431. We want to calculate the theoretical yield of Ti, and what is the percent yield if we basically produced 5.42 times 10 to the 6 grams. I think the only other number you might need is Ti, which is, I think, 4788 grams per mole. All right, so take some time here. We're looking really for two answers. One is theoretical yield of Ti. Second one is what would be the percent yield if you sort of actually produce there 5.2 times 10 to the 6. So take a few minutes to see what you come up with. Let's take a look and see how we're doing. So first off, we want to make sure we understand sort of what's going on here in this problem. We are given the grams of TiCl4, and we're also given the grams of magnesium. So we're really given the grams of both of our reactants, and because we are given the grams of both of them, we definitely could get to the moles of both of them. And because we could get to the moles of both of those guys, that pretty much tells us that this is a limiting reagent problem. And again, what that means is, as we've been talking about, you do need to, at some point, figure out which one is the limiting reagent. Either do sort of your ICE table, your separate calculations to products, you're figuring out from the reactants which one it is. Whichever method you want, you do need to sort of figure that out and obviously do it. And that's because ultimately we are looking for the percent yield here. And remember that the percent yield is the actual divided by the theoretical times 100%. In this particular case, they already gave us the actual yield, so we have that, but we do not have the theoretical yield given to us, so we do need to do basically a stoichiometry problem here to figure it out. So with that being said, regardless of sort of which method you choose, pretty much most of them are all kind of start the same. You need to have a balanced equation, which I do see sort of numbers there. So I'm assuming they're balanced. You do want to convert whatever they gave you into moles. So in this case, we want to convert these grams into moles and the grams of the magnesium into moles. So I'm just going to do that right here. So our moles of TiCl4 would be, and even though they're big numbers, everything's really the same, except you just got some bigger numbers to work with. 2.46 times 10 to the 7 grams of TiCl4. They were nice enough to give us the molar mass there in the problem. Obviously, if they did not, you would need to go to the periodic table to get that number. The 189.7 number, again, would come from the periodic table, your Ti plus your 4 chlorines there. And if we do that, again, we are using our exponent button here, so we don't add any problems to this calculation. 189.7 put 189, not 489. That would also help probably. And that does give us, looks like I'm just going to do a little rounding here to 1.3 times 10. 1, 2, 3, 4, 5, I think, moles of TiCl4. Again, we're going to do the same thing with our magnesium. So we're just going to get our moles of magnesium, which would be 1.13 times 10 to the 7 grams. Again, they gave us the molar mass of magnesium, but if they didn't, you would go to your periodic table to get that. And again, using our exponent button would get us, it looks like, 4.65. 4.65 times 10 to the 5 as well, moles of magnesium. So this is really your starting amount of both of those, right, in terms of moles in this particular problem. Any questions on that so far? All right, so again, I'm going to do the ice table approach here. So again, you can see it a couple more times in case you kind of like that method better. Again, if you chose a different sort of method, one you maybe learned before, or the couple other we talked about, which is probably one of the ones you learned before. In the end, we all should end up really at the same location. So let us give me something fresh to write on here, move a couple things. So I'm going to start with just rewriting the equation here. So that is TiCl4 plus a couple of magnesiums going to Ti and a couple of those guys there. All right, so remember initially we're just going to put in our moles of each of those that we calculated. So we just did TiCl4, and that was 1.3 times 10 to the 5th. And again, remember, it is moles we're dealing with here. Magnesium was 4.65 times 10 to the 5th as well. And remember, in our situation here, it is safe to assume, and in a lot of situations, it's safe to assume that you are initially starting with nothing of our products. Again, we haven't sort of made products at this point, so we have zeros for that. Any questions on that there? Really, the kind of most important part of this ice table is the change part. And we're going to use our same assumption that we talked about, that we would expect this reaction to go from reactants to products, which again means that we do need to use up some of our products, which means that some of our reactants, use up some of our reactants, which means it should be negative and decreasing, while our products should be increasing here and should be represented by a positive. This is also where we take into account the stoichiometry, the mole-to-mole relationship, the coefficients. So again, that is an extremely important part of this. This would be minus x because the coefficient is 1. This would be minus 2x because the coefficient is 2. Again, minus is because they're decreasing. Coming to our product side should be increasing, so positive or plus. Again, coefficient is 1, so just x. Positive on our second guy, coefficient is 2, and x. And again, putting those coefficients in there basically takes care of that traditional mole-to-mole relationship that you do in a stoichiometry problem. Any questions on this change part of the table there? All right, made a big table there, huh? All right, so again here, we're just going to carry everybody down. And for simplicity's sake, I'm going to get rid of the moles part. Just remember that we are talking about moles at this point. X and X. So this is the part where when we do this sort of ice table, we're going to basically figure out which one's the limiting reagent. So we're going to set basically both of our reactants equal to 0. So if we do that, again, we're just going to kind of set that guy equal to 0, which gives us an x is 1.3 times 10 to the 5. We're going to basically set this guy equal to 0. That's going to bring our 2x to the other side, basically divided by 2. And x would equal 4.65 to the fifth divided by 2. Looks like 2.33 times 10 to the 1, 2, 3, 1, 2, 3, 4, 5 to the 5 there. Let's see. Yes, it would. Thank you very much. I should have carried it down. So I think you're talking about here. So it should be 2x. Yes. Thank you. Got it above. I just forgot to drop it down there. Thank you. So yeah, so this one should be 2x. Obviously, we're just bringing down what's above it. So it looks like I missed a 2 there, but definitely should be 2x on that one. All right, at this point, what we're looking for, remember, is it's going to be the smallest number, the smallest x value is our limiting reagent. So in comparison of these two numbers, we see that this guy is our smallest, which means that this guy is our limiting reagent. It means we really don't need this calculation. And that tells us this is our limiting reagent and that is our excess reagent. So again, by doing this, we're able to basically determine those two things. And again, the benefit of this, just a reminder that the x value that we got going here is pretty much all these x values. And that's sort of the basis of that that's going to allow us to pretty quickly now hopefully get to our answer. So we will focus in obviously on what the question was asking, which is what is the theoretical yield of TI? So if we go to our ICE table, we can see that at the end, TI is equal to X. And what that means is that the moles, because we're dealing with moles here, the moles of TI would equal X, which in this case we have now solved for, which is 1.3 times 10 to the 5 moles of TI. And if we want to know the grams of it, we could use the molar mass of TI, which I think I put up there on the other page, and we would get from the periodic table, which is 47.88 grams per mole of TI. And that would tell us that we would produce 6.22 times 10, 1, 2, 3, 4, 5, 6 grams of TI. That would be our theoretical yield. First off, any questions on that so far here? Now, to finish the actual question that was asked, which is what is the percent yield, which is again our actual divided by our theoretical times 100%. Actual coming from the problem, which if you remember back in the problem, it told us that we produced 5.42 times 10 to the 6 grams. So again, that comes right here from the problem. Our actual yield was given to us, and again, usually given to you in most problems. We're then going to divide it by our theoretical yield that we just calculated and times it by 100%. And we end up with call it 87.1% yield. Not terrible, I suppose. Any questions on that? Now that answered the questions that obviously we were asked about in this particular problem. Hopefully you could see it wasn't too bad to get there. But again, just to illustrate, sort of other things that you could figure out at this point from this table in a relatively quickly fashion is, for example, what happens if we were interested also in how much of that guy we produced, the magnesium chloride. Now that I do have the 2x on the bottom there, we see that the moles of magnesium chloride is equal to 2x, which means we can again take the 2 times our x value, our 1.3 times 10 to the 5th moles, and that would tell us that we would have produced in terms of moles 2.60 times 10 to the 1, 2, 3, 4, 5 moles of magnesium chloride, which if we look up the molar mass of magnesium chloride on the periodic table would be 24.31 plus 2 times 35.45 for our chlorines. We would find the molar mass of magnesium chloride as 95.21 grams per mole. And if we take that and times that by 2.6 to the fifth, we would see that we would produce something like we'll call it 48 times 10 to the 1, 2, 3, 4, 5, 6, 7 grams of magnesium chloride. And that would be our theoretical yield of magnesium chloride in this particular case. We could kind of do that relatively quickly there. I think so, if I did that right. I'm going to try that again. It's mg, just make sure I put the right number in there, plus 2 times 35.45 equals that, yeah, 95. There we go. And it was 1.3 per. Any questions on that there? Now, in addition to that, the last thing that's, again, very commonly asked of you is, you know, how much of our leftover would we have? Of our leftover excess reagent what we have. So we could do that also relatively quickly here using our excess reagent. And then remember, in this case, our excess reagent is our magnesium. So we see that moles of magnesium left over from our table there is 4.65 times 10 to the fifth minus 2x, which means it is 4.65 times 10 to the fifth minus 2 times our x value. And if we do that, 4.65 to the fifth minus 2 times 1.3 to the fifth as well gives us 2.05 times 10 to the fifth moles of magnesium that's left over. We then obviously can take that number and times it by the molar mass of magnesium from the periodic table. 2431 grams per mole. That looked pretty bad there. That one more time here, 2431, there we go. And if we take that times 24.31, gives us about 4.98 times 10 to the 1, 2, 3, 4, 5, 6 grams of magnesium left over. Any questions on that? Obviously, we started with whatever we started with there, 1.13 times 10 to the 7 grams magnesium. We have about 4.98 left over times 10 to the 6. So you can see, again, you could very quickly answer all those other questions that may be asked. You can obviously answer just the questions you were asked about, but very quickly you could kind of get to all those sort of answers. Any questions on any of those steps there? Now, again, in case you did it a different way or want to do it a different way, I'm just going to run this across the screen and sort of describe the alternative approach there. So again, starting out like we did, figuring out the moles of each of our reactants. In this case, what we're going to do in this approach here that's going to come across the screen in case you want to look at it later is the reactant to reactant approach, where we want to figure out if we want to use up, in this case, all of our TiCl4, how many moles of magnesium would I need to put in there? So this is, again, what we started with in terms of magnesium. This is how much is needed to use up all of the TiCl4, and we would want to compare these two numbers. And upon comparison, we see that we started with 4.65 times 10 to the 5th moles of it, of magnesium. We only need 2.6 times 10 to the 5 moles of magnesium. So what that tells us is, since we have enough magnesium, that is our excess reagent, and by default, the TiCl4 is our limiting, which is exactly what we figured out with our ice table. And what we're then going to do now is go back here and do a calculation using our limiting reagent to our product. And you can see, again, we end up with the same number there, 6.22 times 10 to the 6 grams as our theoretical yield. And obviously we could finish out the problem like we kind of did over there and figure out our percent yield of 87.1. So again, like I said before, you could choose any approach you want. As you can see, you do end up in the same sort of answer when it's all said and done. Any questions on that particular problem there? All right, so let's try another one here just to make sure. So here we're doing 100 grams of each of these guys, and we are wanting to know what is the percent yield if we produce 120 grams there of our product. So take a few minutes to see what you come up with. I'll give you some numbers here, it'll be helpful. Carbon is 12.01. Oxygen is 16. And nitrogen is 1401. All right, so take a few minutes. We're looking for percent yield here, so see what you come up with. Okay, let's take a look here. So here we have 100 grams of ammonia, which is our NH3. We got 100 grams of CO2. And again, we see that we are given the grams of both of our reactants. That means that we definitely are able to get some moles of both of them. And that really is sort of what's going to help you determine that, you know, this is a limiting reagent problem, right? So again, like normal, we're going to ask you at some point, whatever method you're choosing to use, figure out the limiting reagent, because that is what's going to determine our amount of product. We are again looking for our percent yield here, which is again our actual divided by our theoretical times 100%. And then, like most problems here, we are given the actual here. So we do have that. And also, like most problems, we will need to really do the stoichiometry problem there to figure out our theoretical yield. So as we've talked about many times at this point, same starting couple of steps. We are balanced here. I see coefficients, I'm assuming it's right. We are then going to convert to moles here. So we'll just do that up front. So starting with our moles of NH3, we got 100 grams of NH3. We again will need to go to the periodic table, get the molar mass of NH3. So that is a nitrogen with a 1401, and that is 3 hydrogens at 1.008. That looks like a 1703 situation. Grams per mole there of NH3. We're going to take our 100 and divide it by 1703, looking like we get a 5.8, we'll call it 72. 5.872 moles of NH3. We're going to do pretty much the exact same calculation here to figure out the moles of CO2. We will be starting also with 100 grams of CO2. Difference though, obviously we need the molar mass of CO2 here. So that's 1 carbon at 1201 and 2 oxygens at 16 each. giving us 4401 as our molar mass. 100 divided by 4401, we'll call it 2.272 moles of CO2. Again, this is pretty much our starting amounts, right, of each of these reactants. Any questions up to that point there? All right, so again, I'm going to kind of show the ice table method here. So going to recopy my equation. We've got a CO2 and our product here and some water. And again, initially now we're just going to, again, place in there what we just calculated. So our NH3 was 5872 moles. Our CO2 was 2272. 2272 moles. And again, assuming 0 there of our products to begin with. As we talked about, we're assuming this reaction is going from reactants to products, which means our reactants should be decreasing with time. So we're going to indicate that with a minus, the 2 for the mole-to-mole relationship, and x, minus 1x, basically, because of the coefficient. Product should be increasing, so that's going to be a plus x, coefficient is 1, and plus x here, coefficient also 1 on that side, right? That means that we are going to bring everybody down here. Again, I'm just going to get rid of the moles for simplicity's sake here. X and x. So again, this is the part where we're going to set each of our reactants equal to 0. So if we put that guy to 0, that means x is equal to 2.272 moles. We set this guy equal to 0. We're basically just dividing that guy by 2. And that basically gives us 5.872 divided by 2, 2936 moles. In comparison, we see that this x value here is the smallest. And because that's the smallest, that means in this reaction here, the limiting reagent is our CO2. The excess reagent there is our NH3. We don't really need this calculation. And as we've talked about a number of times up to this point, that x is this x, this x, this x, and that x. And again, that's going to allow us to get to what we're interested in, which in this case is this guy right here. And we see that the moles of our product there, urea, is equal to x, which means that is 2.272 moles of our product. And I believe in this case, they did not give us the molar mass of that guy. So we do need to calculate the molar mass of it. So that is 2 times 1401 from the periodic table for the nitrogen, plus 4 times 1.008 for the hydrogens, plus a 12.01 for the carbon, and a 16 there for our oxygen. That means our molar mass here going to be 60.06 grams per mole, and the moles will cancel, and that gets us 2.272, gets us about 136.5 grams of our product. And again, this would be our theoretical yield. Any questions on that up to there? At this point, what's left is to really answer the question, which is our percent yield. So our percent yield being our actual divided by our theoretical times 100%. Actual given to us in the problem, which was about 120 grams. Theoretical we just calculated, which was 136.5 grams times 100%. And again, 120 divided by 136.5 times 100 We'll call it 8791% yield. Not terrible, I suppose. Any questions on any part of that calculation? I didn't do it in this case, but obviously if we want to know how much water we produced, it would also be 2.272 moles of water. Then we could times it by 1802, figure out how many grams of water we produced. We also could go back into here if we wanted to, and again figure out how much of the excess reagent would be left over in moles, and then times it by the molar mass to figure out how many grams that would be. Any questions on how to do stoichiometry problems, limiting reagent problems, percent yield, ice table method, other methods? And let me, again, I think I have worked out the reactant method, if you will. So here, working out this problem using the other method, what we're doing here is we're saying if we want to use up all of our CO2, this is how many moles are needed of NH3 to do that. This again is how many moles we started with. We would compare those numbers. And again, we see here that we do have enough moles of the NH3. That means, again, as we saw in our ice table, the NH3 is our excess, the limiting is our CO2. We then would obviously use the limiting amount here to figure out our product. And again, that would be here. And you can see we do end up with the same amount that we got from the ice table. And obviously we could then finish it up by doing the percent yield calculation like we did as well. So again, you can see you do get the same numbers, it's just your preference. And so the question is, when you calculate the percent yield, do you need to convert it into grams or can you do it in moles? The answer is you could actually do it in either one. So truth be told, if you're calculating the percent yield of anything, you could actually do it in any units you want here. You know, commonly we do grams and grams, but you could do moles and moles. The key is though, they do have to be the same units here, right? So they got to be the same units on top and bottom. So in these examples that we did, the actual yield was given to us in grams. So that's why we went to grams to do the kind of grams divided by grams. But you absolutely could do moles divided by moles. You could even do kilograms divided by kilograms or any other unit. But again, they just both need to be sort of in the same unit. Otherwise, you obviously can't do grams divided by moles. That won't come out right. So you have to make sure they're the same units. Other questions on that? All right, so obviously you need to know how to do stoichiometry, you know how to do basic stoichiometry problems, you need to know how to do, limiting reagent problems, you need to be able to figure out percent yield and all that kind of stuff. Okay. So we're going to talk about just a couple other things before we kind of finish up the lecturing part here, and we'll talk about lab and everything else here in just a second, but just want to kind of get to these topics here. We're going to sort of talk about solution stoichiometry as well, and solution stoichiometry involves obviously solutions. And the difference is when we deal with solutions, we oftentimes deal with volumes and concentrations rather than say grams and stuff like that. So it's important to talk first off about solutions, and we touched upon this I think the other day as well, but let's just kind of go over it here as well. A solution, as I mentioned the other part day, is again really a homogeneous mixture of two or more substances. And homogeneous means that everything mixes okay, everything looks the same throughout. And there really is two parts to a solution, as we were talking about, I think, the other day. The solute, which is the smaller part, And that's the substance that's present in the smaller part. It's usually the stuff that you dissolve. And it's usually the stuff that you dissolve in the larger part of the solution, which is the solvent. So I think we were talking about this in relationship to kind of the difference between the liquid symbol and the aqueous symbol, you know. And a solution gets the aqueous symbol. So as we talked about before, you know, if you took something like just pure water by itself, that again does get that liquid symbol because there's nothing else there but H2O basically. Now, if you take that liquid and you mix it with some sodium chloride that's a solid, the sodium chloride will dissolve in it. And when it dissolves, it will make a sodium chloride solution that will get the aqueous symbol basically. And again, aqueous typically means solution. Again, liquid is just a pure substance as you go through it. So the nice thing about sometimes people are like, how do I know what the solute is and you know what the solvent is? Well, to answer that question is if you know the name of the solution. So like if we had again the sodium chloride solution, the solute would be sodium chloride. If I had a magnesium chloride solution, the solute would be magnesium chloride. So really the name of the solution is the solute. I would say in most cases, as we kind of talked a little bit about and we'll talk more about later, you know, if you have an ionic compounds dissolve really well in water because it's polar. And usually in a lot of cases, the solvent is water. I would say not in 100% of the time is water always the solvent, nor is water a very good solvent for certain things. But a lot of times, you know, if it's ionic sort of compound or something like that, solvent is probably going to be basically water. Now, sometimes when we think about a solution, we think about it in the form of like a liquid in the sort of the liquid state, right? Like a soft drink. In a soft drink, which is a liquid, the solvent mainly is water. And inside that water is sugar, CO2, which is why you got bubbles, right? Those are solutes and whatever else may be in that soda. But something like air is actually a solution as well. You can think of it that way. The major component of air is nitrogen gas, which is why nitrogen is the solvent. The smaller component of air is oxygen, argon, methane, and other gases, depending on where you're breathing that air. You could also have technically a solution that's in the solid state, like we have on the bottom there, which is soft solder, and the solvent is mainly lead, but there's some tin that's in there as well. Most of the time we think about solutions in the liquid form, but you can apply sort of the definition, obviously, of a solution to something that, you know, is in the gas form or liquid form. So when we talk about solution stoichiometry, one really important thing that we deal with is what is known as molarity. Molarity is the most common definition of concentration that we use. Not the only one, there's a lot of other ones that we'll talk about, but molarity really is sort of the big one that we see the most often and use the most often. Molarity symbol is big M, and it does stand for moles of solute over liters of solution. Most of the time, we think of molarity as just moles per liter. You can think of molarity as basically like a formula. And what I mean by that is you technically can solve for any of these three things. So if I wanted to solve for liters, that would be the moles divided by the molarity, which commonly happens in stoichiometry problems that involves solutions. If I want moles, it would be liters times molarity. And in solution stoichiometry problems, this is used a lot. And really, if you think about stoichiometry problems that we did previous to this, basically the first step that we kind of did almost was convert the grams to moles. So in a solution stoichiometry problem, we typically will use the volume and the molarity to get the moles rather than grams and the molar mass to get the moles. So that's a major difference in terms of solution stoichiometry that we'll talk about. But molarity is moles per liter. You do need to be able to obviously rearrange that and solve for it. Now, when you're calculating the molarity or when you're using molarity, you do need to make sure that the top part is moles, bottom part is liters. So a lot of times we're given volumes in milliliters, which requires us to convert to liters. And that is, again, 1,000 milliliters is a liter. A lot of times in terms of the top part, we're given things in grams. And again, that requires us a lot of times to go to moles using our molar mass. When we say we have a solution that is, for example, 2.5 molar sodium chloride, 2.5, big M stands for molar sodium chloride. What does that really mean? Well, we will oftentimes not want to use the big M as the units in calculations. And I highly recommend that when you have the big M there, that you convert it into moles per liter and not just leave it as molarity. Because very often when people do calculations involving molarity and they leave it as big M, they have absolutely no idea like where the volume part is. So volume gets wrong. They multiply when they should divide when they should multiply, and stuff like that. And you can do that because if we did have something that was 2.5 molar sodium chloride, that is the same as saying 2.5 moles per liter of sodium chloride. Number stays with the moles, and it's always 1 liter in terms of the bottom. We technically could do these problems with dimensional analysis like conversion factors, and you could use it as a conversion factor. You could say there would be 2.5 moles per liter, or you could flip it around, liters up on top and 2.5 moles on the bottom. So I highly recommend that when you're doing molarity that you do convert out of big M and into moles per liter. That way you can clearly see, what is happening in terms of the units, and not forget about the volume. Any questions on that? Now, typically speaking, if you are trying to get to moles and you have the molarity and the volume, do you have to convert it to liters? And the answer is yes, because if you take liters times molarity, you do get moles. If you take milliliters times molarity, you do not get moles. You get what are known as millimoles. So there is a difference. So when you're using molarity by itself, you do need to make sure the volume's in liters to get the moles, because that's usually what you're looking for. Because the most common unit, obviously, of molarity is moles per liter, but molarity can also be known as millimoles per milliliter. And that's why when you multiply molarity times milliliters, the milliliters cancel, but you're left with millimoles. So sometimes people think you could just multiply milliliters times molarity by itself and you get moles. You don't. You actually get millimoles, and you will be off by that factor of 1,000. So again, molarity and volume, if you're doing a calculation involving those things by themselves and as kind of a separate calculation, volume does definitely need to be converted to liters for everything to cancel out correctly. All right, why don't you try one on the bottom there? What is the mass? So we're looking for how many grams of Ki are required to make 500 milliliters of a 2.8 molar solution of Ki. Potassium is 3910, and iodide. Iodide is something. What is that? 126.9. 126.9. All right, take a couple minutes, see what you come up with, and we'll talk about it. All right, let's take a look and see how we're doing on this one. So Again, you can think of molarity as like a formula, obviously, and you can think of it as, all right, obviously we're dealing with molarity. What do we got going on there? So molarity is moles per liter. In this case, I have 500 milliliters, which is in milliliters and not liters, but it basically is a volume. And I do have the molarity given to us. So again, if you weren't sure where you should go to moles. Obviously, once we get moles, we then can go from moles to grams using the molar mass. So if we rearrange that, the moles would equal liters times molarity. Again, as we were just talking about, we don't want to multiply the 500 times the molarity. Otherwise, again, we're not going to end up with moles, which is what we're looking for. So we do need to do that conversion. And obviously, as we talked about, there is 1,000 milliliters in a liter. So you can move the decimal place 3 places to the left, or divided by 1,000, and you get 0.5 liters. Again, as I mentioned before, it's best not to leave it with that big M. And what that basically means when we see 2.8 big M Ki, it basically means we have 2.8 moles per liter of Ki. And it's best to kind of use it like that. You can kind of use it like that, do it as a dimensional analysis sort of problem. And if we did that, we would have our liters, which is 0.5 liters, using this like dimensional analysis and like a conversion factor, really, moles per liter of Ki. Liters will cancel, and that will tell us that 0.5 times 2.8 looks like 1.4 moles of Ki would be needed. We want to know how many grams that is, so we need the molar mass of Ki, so we can just add those together. 3910 plus 126.9. Guess it's a 166 looks like. And again, multiplying really by the 166 grams per mole Ki. Moles cancel, gets us, looks like about 232 grams of Ki is needed. Any questions on that calculation there? So what does that mean, that number? Well, that number really means that if you were to make the solution, you should scoop out 232 grams of potassium iodide. You should put it probably in enough water, since it's ionic, to make a grand total of 500 milliliters, get it all dissolved in that 500 milliliters of water. And at that point, if you mix it up really good, give it a shaky, mixy, you will end up with a solution that has a concentration of 2.8 molar. Any questions on that there? All right. So when we do make solutions, here's a fancy way of making solutions. We sometimes use this guy here. This is a volumetric flask. Volumetric flask. It's a proper way of doing it. Volumetric means expensive, and it's expensive because they typically have one marking on them, and that marking represents the volume, for example. So you can see, you take a little bit of the solid, put it in there, or you could even put a little bit of it into the beaker and use some water, pour a little bit of water or something into it, get enough of it to dissolve. An important note, if you ever do use a volumetric flask, you can see that they did not fill it all the way to the line to start with, because you want to keep it about halfway full with water. Close the lid, start shaking it to get it to dissolve. When pretty much all of this is dissolved, or you slowly keep adding water and you finally get it all dissolved, then you want to go to the line where the meniscus again ends up there at the line. And again, at that point, you would cap it, give it some mixes, and you should have a solution of the proper molarity. You want to be really careful when you use something like a volumetric flask, you don't go over the line, because very common thing that occurs, and I guess it's good you're not physically doing the experiment next week, because this is usually the experiment where it happens, an experiment, and people go to fill it up and they kind of, maybe miss the line and go, oh, is that, can I just dump it out at this point? I just dump out the excess. And the answer is no, that's not a good idea, because at this point, all of your solid is dissolved, which means if you jump the line and you dump out all the excess, you're actually dumping out some of your solute that you started with, which means this molarity of the solution is not going to be correct. So it's a very common thing that occurs in person when people use something like a volumetric flask and they're making a solution. They're like, I'm going to be careful, and whoops, kind of went over. And they bring it to me and go, I kind of went a little bit over, like that much. And is that a big problem? So the answer is no. You typically should remake the solution, depending on the application, but you really should remake the solution, because the purpose of using something like a volumetric flask like this is to pretty accurately, and precisely sort of make your solution there. And obviously, if you went over and you poured the excess out, you're actually losing some of your solute, and it would not be correct. So keep that in mind if you are in person and you are using a volumetric flask to make solutions. The line really does matter. So usually what you do is you fill it up, to like about here, maybe. Get a medicine dropper, a little pipette, something that you can really control the amount of water, and then go really slow until you get it to the line. That way you don't go over it. And there's no other markings on here, so you got to hit that line exactly on the nose. Most of the time, though, sometimes people will just make solutions in graduated cylinders. Beakers is not the greatest thing to make them in, but graduated cylinders sometimes people will use and stuff like that as well. Why don't we try another one? What is the, why don't you try this one? What is the molarity of a solution that is made by dissolving 42.5 grams of calcium chloride in enough water to make 250 milliliters of solution? All right, so take a couple minutes here and see what you come up with. Calcium is 4008. Chlorine is 3545 grams per mole. All right, take a minute to see what you come up with. So in this case, we are looking for the molarity. So obviously that is moles per liter. And that basically means that we want to see if we have any of that information. So we have 42.5 grams, not in moles, but we definitely can get to moles from that. We have 250 milliliters, which again, not liters, but we can get there. So we really have everything we need to get to molarity. We just need to do a few conversions here. We'll start with the maybe easier one, which is there's 250 milliliters. There's a 1,000 milliliters in a liter. So again, those cancel, gets us 0.25 liters. We then want to convert our grams of calcium chloride into moles. So we do need the molar mass of this guy. So that again is 4008 grams per mole for the calcium, 2 times 3545 for our chlorine there. So that is 2 times 35.45 plus our 40.08. And that's, we'll call it, we'll go 111 on that rounding there. So we will do 111 on the bottom there. And that's going to get us 42.5 divided by that. Gets us 0.383 moles. We now have both of the things that we need. So the molarity would be 0.383 moles divided by 0.25 liters. That is going to get us, we'll call it
1.53. And the answer here would be 1.53. The units don't cancel, so moles per liter, or you could write 1.53 big M. Question on molarity, or how to calculate molarity, obviously is the most common concentration unit. It's one we use the most. Any questions on that there? Okay, so I think what we're going to do is we're going to lay it up there for the lecturing part here.